right, so we did one example of the deformation for axial stresses, for axial load. We did one yesterday for axial and bending. No? Okay. So today we're going to do another example. A little bit more interesting, but this one, we're going to try to introduce the shear, okay, the deformation due to shear. So in this part, we're going to have bending, so bending moment and shear. So in this part, we consider like a wind box. So let's see, I can do this. Right, so let's see. It's gonna go, let me just do another one here. All right, I'm gonna connect. Okay, and let's connect this one here in the middle. So let's say we have some type of wind box, which is fixed at one end. All right, so in here we know there is a force Vy equal to 44,500 newtons. Coordinate system here is going to be Yx and Z. Okay, and the nodes will be 1, 2, 3, 4, 5, and 6. All right. So maybe I'm going to do a little sketch. I don't want to put too much on the same figure. So let's see. We know that the Young's modulus for the system will be 69,000 Newton millimeter squared. The torsional modulus will be 25,900 Newtons millimeter square. Then we're going to have that B1 equal B3 equal B4 equal B6 equal to 650 millimeter square. B2 equal B5 equal to 1,300 millimeter square. Okay, and I'm going to do another small figure here. Just to give the dimensions. So that distance over here is 250. All these will be in millimeters. So it's 250, 250, 500. Okay, and let's say Vy, I'm going to say here Vy apply a shear center. So I selected this problem for, two reasons. One, to do the example for the strain energy to shear, but then because Dy is applied at the shear center. And most important, that's not new, but this time the cross section is not fully symmetric, no? Yeah, so let's see what happened with the induced shear flows. Okay, so the question is to determine the deformation at the free end. Okay, so over here, since we're doing strain energy and energy methods, what type of loadings are you gonna have over here? This force over here is gonna induce what? You have a force at the top of a beam, is gonna induce what? It's gonna induce, what's gonna happen to this? It's going to bend up due to what? Due to a bending moment, no? Okay, so the Vy is going to induce a bending moment. So Vy induces a bending moment plus what? Vy induces shear flows in the, I call it the wind box cross section, but I'm just calling it cross section, no? All right, so in order to symbolize everything, what would be the total strain energy of the system? So if we look at the energy, which is what? Generally is stress. So this is the general expression. For strain energy, we need to look at the component due to bending, which would be what? M squared over EI dz plus the 1/2. This one is a bit more complicated. So 0 to L. Then we need to go through the cross section of Q squared over GT ds. And then we integrate along the whole length, that would be dz. So in other words, this will be the due to bending, and this is due to shear. Okay, so basically the same thing as we did yesterday. We had this term, but instead of having this one, we had the one that was P squared over EA, no? Okay, so in order to find the deformation, so let me go to the next page. So deformation is obtained by applying Castigliano's second theorem or principle, I don't know how we call it, which basically was what? Q sub I is equal to the partial derivative of the strain energy with respect to the force at that location. So this will give us what? So the first term will become what? partial of M partial Q, so M sub I, Q sub I. So should I do it differently? It's fine. We can do it that way. M I over EI dz. Oh, I forgot to put something on the figure. Plus partial of what would be here Q sub I. Oops. Should be actually the double integral. So, all right. So let's do this. We're gonna have here a bigger interval, so it would be partial Q sub I GT ds, and then this would be dz. So this will be deformation due to bending moment, and this is deformation due to shear flux. Okay, and let's go back to the first page here. I forgot to put the length of this wing box, and L over here will be 2000 millimeters. Okay. Okay, so basically, I mean, let's say your intuition. Which term do you think is going to have a much bigger influence on the deformation? The bending or the shear? Probably the bending, no? Okay, all right. So basically, we need to calculate the deformation due to the bending and due to the shear. So if you remember in this equation, the Q sub I, you need a force being applied at the location when we're going to calculate the deformation. In this case, is it a force applied at the free end? V sub y. So let's, for simplicity, we're going to say Q sub I equal to V sub y in this case, no? We're going to calculate that the deformation there. So let's over here. So taking Q sub I equal Vy for simplicity, okay? We don't even know what is applied, okay? But we know we'll be at the free end, okay? Otherwise, well, if we really wanted to calculate the deformation at 1, then what should we do? We should put a fictitious force over there, no? But I don't want to do that, okay? So there's no good yet. Okay, so all right, so let's first find what is the deformation due to bending, and then we do the one due to shear, okay? So the one to bending is the easy one. The one due to shear is the one that requires a lot of work, all right? And it doesn't add much to the result, but it is what it is, okay? So let's first determine the deformation due to bending. Let's say pure bending. It doesn't matter if you just put bending, okay? I had some space. All right, so in other words, we're going to say Q1 in our case is just will be the term so this will be the term that we're going to do, and this will be between 0 and L. Okay, so if we look at our problem, we could simplify it as what? Really, we have what? If I just do a very simple sketch, we have a force V over here, and we know L over here. So if you had to do, instead of doing the cut and so on, okay, I'm going to start doing it a bit faster. If you had to do the free body diagram for the moment, what would that be? So actually, this is pushing up, so the reactive moment is going to go down, no? Okay, so really should start from the negative value. It should not matter. It's not going to matter, okay? So it's not going to be 100% accurate, but what would be the moment maximum? Where? At the tip or the root? At the root. So we'll be here, should be smaller, and then what should be the value at the tip? 0. So basically, we have a straight line, no? Okay, that will be equal to Vy. So if we start the reference frame here, in order to be 0 at the end, what should we put over here? Would that work? No, because it will be maximum at the tip, no? So in order to make it 0 at the tip, what should we do? Minus L. Okay, and if you want here you can put plus minus. Really should be negative, but it doesn't matter. At the end, it's not going to change anything. So it's fine if we leave it as positive. Okay, all right. So we get that. So basically, what does that mean? In the above equation, we have Q sub I equal to Vy, and we know our M sub I is going to be equal to what? Vy times Z minus L. So we have the expression for the bending moment in function of y, which is our Q. So basically, we can go and substitute into the equation, okay? So that we're gonna have, so substituting into, let's say, lowercase a, what are we gonna have? We're gonna have Q1 equal to 0 to L partial M1 or Mi find Q sub I, M sub I, dI, dz. So this is gonna give you, so if we take the derivative, what would that be in function of Vy? So this will be, space to write everything, I think. So will be partial with respect to Vy of what? Of Vy Z minus L times Vy Z minus L divided by Ay dz. So what would be the partial derivative of this term over here? Z minus L. So basically we're gonna have Q sub 1 integral 0 to L of Vy Z minus L squared times dz. Okay, so if we do the numerical application, I mean, you all know how to interpret this, no? I hope. All right, shouldn't be Okay, so we do the numerical application. So basically Vy, how much is Vy? I think it's 44,500 newtons. L is 2,000 millimeters. And E, oh, we forgot something here. E is equal to 69,000 newtons per meter square. But what do we need? The I. Okay, I forgot to calculate. I should have done it first, but yeah. We need I. So the I, let's see. I mean, in this case, pretty easy, but about which axis is this bending? Is it bending between the Y, the X, or the Z axis? This will be bending about the Y axis, no? So we need to find the IXX. So I would be really IXX. Okay, that we need to find. So I should have done it first, but we do it now. Yes?
Why is it bending about the y-axis? Shouldn't it be bending about the x?
It's bending about the x.
Oh, sorry, you said y.
No, it's bending about this one. So we need to find the IXX. It's bending about this one, the x. Okay. So basically we need to find IXX. So in order to do that, I'm gonna redo a quick figure here. Okay, so IXX should be equal to what? To the summation of what? The B sub R's Y sub R squared, no? That we have done before. So here, I mean, because by geometry, by symmetry, I mean, B3 is equal to B4, B2 is equal to B5, B1 is equal to B6, no? So, all right, we can save some time. So what would be that distance here? This would be Y here. The Y starts from here. So, all right, let's maybe write it down. So this is so we have the values here for B1. So this would be what? From 1 to 6. Since we have time, let's just do it. So this would be equal to what? B1, Y1 squared plus B2, Y2 squared plus B3, Y3 squared plus B4, Y4 squared plus B5, Y5 squared plus B6, Y6 squared. So let's see, this should be equal to what? So what was B1? Let's see, we have B1 equal B3 equal B4 equal B6. So we can have 4. What is the value for B1, B3, B4, B6? Is 650. What is the distance between 1, 2, 3, 4, 5, 6 and the neutral axis? Will be plus minus what? 125 squared plus 2 times B2, B5, that would be 1300 times again plus minus 125 squared. So if you do this, I can give you the result. Yeah, the all this stuff there, but if I remember properly, is I'm going to check, but I think it's 81.25 10 to the 6 millimeters to the 4. All right, so again, I did all this stuff on Maple. So the thickness of the wall is 2, all of them. Forgot to put it. So where is IXX? Did I calculate IXX? Yeah, 81.25, 1, 2, 3, 4, 5, 6, okay? All right, and if you want, we're gonna need it, just at the end. Forgot to put here on the figure, the thickness of all the walls. The wall thickness of all the walls here, T, is 2 millimeters. So all of them have the same thickness, okay? All right. All right, so okay, so basically we're gonna have the end that Q1 will be equal to the integral 0 to L equal to 1000 of Vy, which is 44,500 divided by a lot of stuff, divided by 81, divided by 69, 10 to the 3, times 81.25, 10 to the 6, times what? Z minus 2000, everything square dz. This gives you that Q1 gives a deformation. I did it at the end of my Maple. I did at the end, reverse to what we're doing in class. Gives me 21.17 millimeters. This is giving me an idea for the exam. So, all right, so we did the one for the bending. So next, let us find the deformation due to shear flows. So let's call that one Q sub 2, and the expression will be what? So we have a big integral 0 to L, then we have a cross-sectional integral will be partial Q sub I, or partial Q sub I over GT. Yes, and this will be dz. Okay, so again over here, Q sub I equal Vy, Q sub I to be determined. To be determined in function of Vy. Because remember, when we take the partial derivative, we need to have this in function of Vy. So that's why you needed to use Maple. Otherwise, I mean, you don't have to, but if you do one mistake, it's going to take you some time to correct it. All right. All right, so let's go. So how do we find the shear flows? We need to take the cross section. We need to make cuts. No, we need to calculate all the expressions. So here we go. All right, so 108. So we need to find shear flows. So this is a good practice for the exam because probably you're gonna have to do this. I mean, I still haven't decided the problem, but probably you're gonna have to do it. All right, so what is our cross section? Okay. Let's say this will be our cell 1. So I'm going to call it here Q sub 1, and this will be Q sub 2. All right, so in this case, the expression for Q will simplify to what? I think by now you know that one by memory. It's minus Vy over Ixx, summation of the B sub R, Y sub R. Okay, you have done that enough, no? Okay, so we need to start from 1 point. So which point you want to start? So I'm just looking here to see if I have the result I'm gonna have to go. So let's say you want to do it by cell or just want to go by order? I mean, can go by order if you want, okay? So let's see how I did it on the Maple. That way we can see the results faster. I'm not going to use that. So let's see what I did here. Okay, I went by order. All right, so let's do that. There we'll have the results. So let's do Q12. Q12 is 0, no? Because it's a cut. What would be Q23? 0, there is a cut. Okay, now I'm going to put something. I mean, I know this stuff, we can make it very quick, but this is not that important for this figure, but just for the understanding. Okay, which one, now that we do this, which one should be the elements that carry a load? It should only be 3, 4, 2, 5, and 1, 6, no? All the other ones should be 0. So that also helps us to validate. So this should be 0, this is 0. Then you can do by symmetry 0 and 0, but let's see what the math is going to give us. So then we do Q34 should be equal to what? Should be equal to Q23. So this should be equal actually to 0. This should be equal to what? Q23 minus Vy over Ixx V3 times Y3. Okay, so what about you give me the values? Please take your calculator because I'd rather do your calculator. So this should be equal to what? This should be equal to, let's do here by line. Should be equal to minus 44,500. I want to check. Divided by Ixx, we found to be equal to 81.25 10 to the 6. What is B3? B3 is equal to 650. And Y3 is 125. And all this is Vy. So can someone do that calculation, please? Okay, so it gives Vy over 1000, which is good. I wanted you to check this value here because I didn't know if it rounded off, but basically that's what we get here, no? And it should be negative, minus 1 10 to the minus 3, no? Okay? Vy. All right, so now we can follow the other ones. All right, so then we do Q45. Should be equal to what? Q34 minus Vy over Ixx times V4 times Y4. So in this case, what's going to happen? In this case, instead of being positive 125, this is going to become negative 125, no? So we're going to have this value in positive. So this is going to be equal to 0. Yeah? I don't need too much to give too many details. Okay? So here we're going to get Q45 equal to 0. So the ones I'm interested in is basically these final values here. I mean, I can do a table at the end, a summary. All right, Q45. So now for, okay. All right, we can do now Q25 if you want. Even though since everything is 0, it's not going to change too much. So this should be equal to what? Q12 plus Q23, but both of them are 0, so it doesn't matter. Minus Vy Ixx B2 Y2, no? Okay. So anyway, you know, this one is 0. This one is 0. B2 is twice the value of the other one. So I'm guessing this should be equal to, say it, twice the other one should be negative 2 divided by 1000, no? Okay, which is what we get here. So negative 2, because Y2 will be negative 125. So we get Q25 equal to negative 2 over 1000 Vy. Okay, do I need to put over here? Yeah, I don't think so, but since we are, Y1 equal Y2 equal Y3 will be equal to 125. Y4 equal to Y5 equal to Y6 equal to minus 125, no? I mean, you don't have to put it. I think it's pretty straightforward, but, and I mean, since we are here, let's put the B values since I'm doing it. Everything is on the first page, but B1 equal B3 equal B4 equal B6 equal to 650. B2 equal B5 equal to 1300. Okay, at least other data is on the same page. All right, so now that we have Q25, we can go to Q56. So Q56 is going to be equal to what? Q45 plus Q25 yeah, minus Vy Ixx B5 Y5. I mean, what should we get? I let you do the calculation, but this should be what? This should be what? B5 is the same as the B2 we just calculated, no? B2 equal B5. But instead of having the Y equal to positive 125, is the negative 125. So it's just gonna, this one is gonna cancel this one, no? Yeah, okay. So we get Q56 equal to 0. All right, then what else do we have? Q61 is going to be equal to Q56 minus Vy over Ixx V6 Y6. So what should that be? Should be the same thing we got for Q34, but on the negative side, no? We had here Q34 was -1, 0 will be 1, no? Because we have minus, here we have minus, minus, positive, here we only have the minus side. Yeah? Okay. So this should be equal to Vy divided by 1000. So this is going to make everything a lot easier. That we have these easy values. Okay, let's see if the next value is also easy. So 105, 106, 107, 108. Okay. Okay, so now comes the thing that might be a little bit new. I mean, should not be new, but okay, so Vy what do we know? It's applied at shear center. Okay. Do we know the location of the shear center? We don't know the location of the shear center. Again, we could calculate it, but we don't need it. So we go around. So, all right. So what do we know? If the force is applied at the shear center, Vy applied at the shear center, which implies that the angle of twist of the two cells is going to be equal to 0. Yes? Which implies that d theta dz of cell 1 equal to 0, and which means that angle of twist of cell 2 is equal to 0. Yes? What is the difference with the problems we did before, where we did not specify where Vy was applied? Instead of writing this equal to 0, we're saying what? That the angle of twist will be equal, correct? And we have, how many unknowns we have here to determine? 2, Q1 and Q2, no? So since we only had d theta, the angle of twist of the first cell equal to the angle of twist of the second cell, that was giving you one equation. We needed to go and apply the summation of moment external equal to the summation of moment internal. Yeah? Do we need to do that in this case? We have two equations, no? Yeah? So we can go and solve. All right? So here, let's see if I remember the expression where d theta dz, what was this equal to? I don't want to make, I think I know it, but I don't want to make a mistake. So let me go and check. Okay, so we went to find the equation for d theta dz. So it's over here. All right, so this is what we have. So basically, we're going to have one equation. So we're going to have, so let's say this will give us equation 1, equation 2. Okay, so let's see. All right, so let's write it down. Should be equal to what? Should be equal to 1 over 2 A1 GT. All these terms are constants. QDS. Okay, so this is going to give us what? 1 over 2 A1 GT. And now, what do we have over here? So maybe let's do a small figure over here. Maybe not that small, but let's just do a figure. Okay, so let's see. We know Q12 is 0. This is 0. This is 0. This is 0. What do we have for Q34? Q34 is negative minus V1 over 1000, no? But what does that say? Is that instead of going down, it's going up, no? Okay. Then what about Q25? Q25 is also negative, so it's really going up. So let's see, this one was equal to Vy over 1000. The other one is Vy over 2000. And then Q61 is also going up. And it's equal to Vy over 1000. If you want to zoom in now, but let's not forget that each one of these cells will have what? Become squared. This would be what? Q1 or Q2? Q1. And this one will also have here Q2. So sorry for that, but this is important. So okay, so over here, let's start by the Q1s because otherwise I get lost with this stuff. Okay, so we do here Q1. Q1 will have an effect through ds, no? So which one should that be? Should be S23 plus S34 plus S45 plus S25. Okay? I'd rather do it this way. It's a lot less confusing. What about Q2? This one is going on the opposite direction, no? So minus Q2 times what? S25. Now we need to take into effect the values for the Q23 and so on, no? So do you want me to write Q23, S23 eventually 0, or you want me just to omit it? I will just omit it? Yes? Okay. So now we need to take consideration the other one. So now this one is not creating anything. Now this one, be careful. You take the magnitudes as they're over here. So this one should be what? Positive or negative? To go everything on the same, to go everything counterclockwise. This one will be creating what? A negative angle of twist, no? So you should put here now minus, put it here, minus Q34 S34, but make a note. What is Q34? Q34 is the By divided by 1000. It's not the negative value, no? Because already I do from the figure, okay? All right. What else? Q45, 0. Now Q25 should be positive, no? Plus Q25 times S25. Any question? I mean, I rather do it this way because to tell the truth, every time I try to use the Q sub B and so on, I always get something wrong. And this way I get it right, okay? I break it up, I do it from the figure instead of just math. So now we do the second one. And d theta dz of the second one will give you what? 1 over 2 a sub 2 gt integral qds. Oh, maybe let me add one thing over here because since I don't know which color to use anymore. Let me just put it over here, okay? What would be A1? The area of this cell, no? So it could be S12 times S25, okay? And A2 would be what? Oh, it's the other way around. So this should be the A2. And A1 should be S23 times S34 or S25. Yes, it's just the area of the cells, no? Okay. T is constant over time. So, okay. So for the second one, what are you going to have? One over 2 A2 GT. Let's do the same thing. Let's start by the Q1. Will the Q1 be now positive or negative? If we do counterclockwise, the Q1 is going up, no? So it should be minus Q1. I'm using that in blue. Minus Q1 times what? S25. Now let's do the Q2s. Plus Q2 will be going all around the cell. So you can start whatever you want. S12 plus S25, if I start from that corner, plus S56 plus S61. Okay. All right, so let's start about 1, 2. Is Q12 going to create any twist? is 0, no? So it's not doing anything. What about Q25? Is it going clockwise or counterclockwise? It's going to create a clockwise, so that's negative. So we'll have here minus Q25 times S25. Remember, you need to take the magnitudes from here. So I went 1, 2, 2, 5, 5, 6, 6, 0. What about 1, 6? 1, 6 is going counterclockwise, so that should be positive plus Q 61 S 61. Okay, so this will give you some simplified equations. So let's say, okay, dividing, no, so multiplying, actually multiplying equation 1 you don't need to put this, but since that's the way I did it. That's the result that I have. Okay, that's why I don't want you to do the calculation and get all word. So you're gonna get that d theta dc1 equals 0. Gives me the equation of by divided by 1 million, so 10 to the 6, plus 3 Q1 divided by 500 minus Q2 divided by 1000 equal to 0. So this will be our equation 1. All right, and the 7th equation, d theta dz of 2 equals 0 is giving me minus dy divided by 50, 10 to the 4, minus Q1 over 500 plus Q2 over 125. All right, so now we have, and here what's important is what? Is that these equations, they're still in function of Vy, no? So now we can solve these two equations for Q1 and Q2. All right, so solving. For Q1 and Q2, what do I get? Q1 equal to So that's basically what I did over here. That's the equation I just gave you. That's the one I copied. So Q1 equal to minus 1.3 10 to the minus 4 Vy. Q sub 2 equal to 2.17 10 to the minus 4 Vy. 2.70, yeah. So you see that, I mean, you're welcome to do it by hand, but I'm always going to do Maple or MATLAB in order to do this stuff. Okay, so now what does that mean? So now, we need to be careful. I will probably personally do another figure, okay? I mean, this stuff to me works a lot better with figures. So let's see if I do another figure here. One, two, three, four, 5, 6. So from this result, Q1 at the end is going what? Counterclockwise or clockwise? We got a negative value. So what does that mean? It goes clockwise, no? What is Q2? Q2 is positive. So that one is still going to go counterclockwise. All right. So now, all right. That what were the values we had? So basically, here we had for the Q. So maybe you can write it down. Q12 was equal to 0. Q230. Q450. Q560. Then Q34 we say was going up. So Q34, I'm not going to have space for the other ones, but this will be Vy over 1000. Q25 was also going up. And Q56 was also going up. So Q61, sorry. So this is Q25, Q61. When I put Q25, the magnitude is Vy over 2000, and Q61 should be the, I think it's the 1000. Q61 Vy over 1000. Yeah. So from figure one, what are we going to get? So let's say the QB12 should be equal to what? Should be equal to Q2, no? Yeah? And Q2 is 2.17 10 to the minus 4 Vy. So we know QB12 in function of, okay, we just call it Q12. Or we just call it Q1, or you want to do the combine. That's fine. Let's do the combine. Okay. We have this. Then what are we gonna have for Q? Let's do 23. B23. What is that going to be equal? That one should be equal to minus Q1, no? So that should be equal to what? So it should be the negative 1.3 10 to the minus 4 Vy, even though the signs are not going to matter. Q QB34. QB34 should be equal to what? Q34 plus Q1. So I don't know, what would that be? I mean, in function of Qy, but you see everything will be in function of Y, no? This is in function of Y, and all these values are also in function of Y. I don't know if I have the results over here. I should, but I don't know. So let's see, QB34, yeah, so will be minus 1.13 10 to the minus 3 dy. I'm going to keep copying here. Q B45 is 0, so that should be equal to minus Q1, which is equal to negative 1.3 10 to the minus 4 dy. QB56 equal to, so let's say look at the figure, equal to Q56, which is 0, plus Q2. So that one should be equal to Q2. Q2 is equal to 2.117 10 to the minus 4 dy. QB61, so it should be QB, so Q61 plus Q2, and this gives what? 1.22 10 to the minus 3 by. And finally, QB25 should be equal to, let's see, so it should be, oops, that one, 25 is going up, so it will be Q25 minus Q1 minus Q2. Yeah, so we're going to look at it. So, okay, so Q25 minus Q1 is different than there, but if you look at the figure, minus Q2, so QB25 will be equal to oops, wait, did I do this wrong? Q61 is, no, 122, okay. No, that's good. And this one will be 1.65 10 to the minus 3 dy. So maybe it looks better here than on my page. This is from the figure, okay? So be careful, it might be different than the Maple file. Do you need this or you don't copy? So 111, let's see how I can rewrite this. Okay, so we have Q1, Q2, everything's in function of Y. So recalling the expression for the deformation due to shear, which was what? Q2 equal to, let's see which order did I use. I think I know reverse the order. Okay, yeah. Partial of IGT. Yes, dz. Okay, so I'm not going to do the hand calculations here, but basically it will be 0 to L. So this should give you here Q2 equal integral 0 to 2000 of, let's see, partial QB12 partial Vy Q12 over GT plus partial QB23 partial V sub Y. This should be QB12 QB23 divided by GT, which is all the time constant. Plus, I mean, do I need to put all of them? I can just put the summation here. To partial of QB, what was the last one we calculated? 25 over partial Vy. Ooh, damn it, I forgot one term. What did I forget here, guys? This term needs to be multiplied by S, no? So this one is times what? S12, S23. This one will be QB25 over GT S25. And here you're gonna have the dz. So if you substitute all this stuff, where are you going, Paul? Where bien? Me too. Doesn't matter. The other day I did not let somebody go. I cannot let you go.
It was an online meeting. I have to be there in person.
But it doesn't matter. You are in class, okay? Rules, the same rules for everyone, okay? The other day I did not let somebody go. All right, so over here, basically this is what you see on this expression here. You see QB12, but I did it differently. I first did the constant term, then I did the partial differential S12, integral 0 to L, okay? So if you do all this stuff, you get that you're gonna get a deformation. I mean, I could give you the expression actually. Let's get this one. So Q2 gives you 13 Vy divided by 23,082.80, which gives you 2.43 millimeters. Okay, and what did I write for the Q1? What was our expression for Q1? So in this one, we can maybe add in this one that Q1 is equal, I'll show you now, equal to 32 Vy divided by 67,275. Okay, so what I've just done is just to add this expression here. Okay, if you want it, you don't need it. I put this expression here. So the total deformation of the structure or wind box is Q total equal to Q1 plus Q2, so equal to 21.17 plus 2.43. Q total equal to 23.59. Okay, so we finish here. What is this one here? This is due to bending. This is the one due to shear, okay? So is it worth the time we spent on the shear for the total deformation? Not that much, no? About, yes, about 10%, yeah, just a bit over. But again, it needs to be done. And in this case, the box will not be twisted, but you still have Q1, Q2 because the box is not, the two cells are not exactly the same size. If they were the same size, what should we get for Q1, Q2? Probably it will be 0, no? I mean, it will be 0, no problem. It will be 0. Okay? Now you can go.